We have completed our introduction in electromagnetic theory by discussing electric phenomena, electricity, and now we turn to magnetism. This next chapter is chapter 27 in our notes, and it concerns magnetic fields. That's the first chapter in the domain of magnetism. And our first section in this chapter is 27.1, which addresses magnetic fields from natural objects in the environment. This is kind of an introduction that's not mathematical, that most people are familiar with from their high school science courses. So we can go through this pretty rapidly. In our early science classes, even in grammar school, we play with magnets and learn about the north and south poles, how the north poles repel each other, the south poles repel, and the unlike ones, north and south, attract one another. This is very much like electricity, where positive and positive repel, negative and negative repel, but positive and negative attract. Now, we've often also in those science courses taken iron filings and put them on paper that's over a magnet, and one can see the alignment of that magnetic field. You may have seen things that look like if you had a magnet underneath the paper like this, you may have seen your filings look kind of like this, where you had a north and a south pole. And those filings give you an indication of how if the filings are always long little slivers of iron, and they line up with the magnetic field. Now, the Earth's magnetic field was discovered with the orientation of certain kinds of rocks called lodestones. These are magnetic types of rocks whose magnetism formed with the Earth's magnetic field when they were liquid and solidified. So you'll have such a rock, and let's imagine our Earth is like this. And here's the North Pole up here and the South Pole here. And people found that this rock would always point in a particular direction. Well, this was incredible technological breakthrough for ocean navigation, because people could tell which was north during storms or cloudy days or nights when they couldn't see the stars, and orient either from the sun or other astronomical bodies. Those lodestones were the first magnets that were used by man. Now, we talk about an object like a magnet where the part that points toward the North Pole is called the North Pole, and the other part is called the South Pole, and that's how we name them. Now, what that means is actually, since north doesn't attract north, but north attracts south, it means that underneath here, this is the North Pole, geographically the South Pole, but there's a magnetic North Pole here, and a South Pole here, and a magnetic North Pole here. That's so that the magnet that points to the North Pole is attracted to the South Pole that's beneath the Earth's surface. And so that can be kind of confusing. So our North Pole actually has a magnetic, I'll put magnetic South Pole there, and our South Pole has a magnetic North Pole underneath. Now, it was discovered that if you have a magnet, like this magnet here, that if charged particles are moving by in that magnetic field, they will in fact be altered in their course of action. A force is exerted on them, and we're going to discuss the nature of that force in just a little while. In fact, it was later then discovered that magnets are very different from ordinary positive and negative electricity. In positive and negative electricity, you have a positive charge and you have a negative charge. These are called monopoles because they're single poles that exist. You can have an object which has a positive charge, and you can have an object, another particle, that has a negative charge. They don't have to come together. You can have one or the other or both or whatever. But with magnetism, it's quite different. There, you cannot have a single North Pole or a single South Pole. In fact, all of magnetism is created by the motion of electrical currents. So just like electrons or protons or other charged particles are altered by the magnetic field, they also create the magnetic field. So all magnetic fields are created from the motion of charged particles. We'll also have formulas that tell us exactly how that occurs. And therefore, there's no single separate North or South Pole. like there is for the positive and negative pole for electricity. The north and south poles appear in pairs, and so the dipole, or the pair of poles together, is all you'll ever find. If you take a magnet like this and you chop it in two, you'll find that miraculously this is the north pole, that a south pole will be right here. And if this was our south pole here, you'd find a north pole in this piece here. So no matter how much you chop them, they're still pairs. The force on a segment in a magnetic field opens the possibility of a motor, which is just incredible, because that means we can send electric current through wires and then force motion to occur, which means that we can take energy that's electrical, generate that electric energy, send it through wires where it's just the motion of the voltage and the electrons, and then actually do work at the other end. We don't have to have a belt or an axle that connects the power plant to the object. That absolutely technologically revolutionized manufacturing, of course, in all of our lives. Now, if you think about this North Pole and South Pole, that means that these field lines go all the way through, and they go all the way through here. Magnetic field lines never stop or start. They just always keep going, and they point in the direction a magnet would point. And since a magnet would point that way, that's the way it points. Points the way that a north pole would point if it were pointing along. So our magnetic field lines go this way because they're pointing like that. Direction of the magnetic field is the direction that we would see a magnet point. So out here, we would see the north pole go this way, attracted, the north pole go this way, so the north pole, the field lines go toward the north pole, and then dive in, going to the north pole that's inside the Earth, and then come out of the south pole like this. And this is the direction of the magnetic field associated with the Earth. The cosmic rays, and we'll draw the Earth again here with its magnetic field lines. Cosmic rays come in from outer space, and it turns out, and we'll see this occurring in the force, that the particles spiral around those field lines, and it drives them into the north and the south pole. Another particle that's coming this way will find that it curves around like a helix, wraps around those magnetic field lines, and they go into the north and south pole. And when they do, that takes the intense radiation that comes from outer space and carries it to the north and south pole. And such radiation is called the aurora, causes the lights called the aurora borealis and aurora australis for the south pole. And through history, the magnetic field has changed, and it's constantly shifting, and at times it's gone to zero. And during those periods of time, the Earth was bombarded by intense radiation that could have caused genetic change and mutations that led to faster evolution during those periods of time. Now, the units for the magnetic field are the Tesla. The Tesla is a very strong, intense magnetic field. And if we look at how much magnetic field the Earth has, it turns out that the Earth has about 1/10,000th of a Tesla, which is called a Gauss. And so a Tesla is 10,000 Gauss, or a Gauss is 1/10,000th of a Tesla. And the Earth's magnetic field is about a half of a Gauss, something of that order of magnitude. So again, the main thing to take away from this is that magnetism differs from electricity in the fact that the two poles, the north and the south, although they're similar to electrical charges, positive and negative, they occur only in pairs, and they occur as a result of being generated by electrical currents that go around in circles, and that creates the magnetic field. All magnets are created in that way. And we'll discover the exact equations for that in just a moment.